I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, Lord, thank you for the students. Just ask you to bless our work today, Lord. In your name I pray. Amen. Yes, I was looking for 7 students, then I looked at Blackboard and I'm like, oh, wait a minute, there are only 6. It's a good thing I didn't wait for the 7th student last time, you know? So, yeah. All right, so let's talk about quotient modules. And homomorphisms. I'll try to just hit the high points here. First of all, I need to just define for you what's a module homomorphism. So if we have R a ring, and then M and N modules, and to be more specific, R modules. To be more specific still, left R modules, all right, like we defined last time, all right. Then we can talk about a map from M to N. And let's agree that M and N will be R modules, and that R will be a ring in the remainder of this lecture, and I will not write those words on the board again. All right, so M and R modules, R is a ring, all right. So M to N is an R module homomorphism if what? If you have 2 things. Number A, phi of x plus y is phi of x plus phi of y. Number B, phi of Rx is equal to R phi of x, right? And this, of course, is for all x and y in the module and R in the ring, right? Okay. So it's additive and in some sense homogeneous, right? I mean, like, this looks familiar, right? If R was a field and the R module was a vector space, this would be a linear transformation, right? Okay. And I won't write it down. What would it mean? What would I mean by R module isomorphism? Yeah, if it's a bijection, then it would be a R module isomorphism. So in other words, if it's both injective and surjective. So, you know, if a R module isomorphism phi from M to N exists, then we say M is isomorphic to N, right, as R modules. This all seems familiar, doesn't it? There are 2 special submodules attached to a given R module homomorphism. What do you think they are? Kernel of phi, which would be what? X in M such that what? Right? Kernel of phi, x in M such that, you know, it maps to 0. This is a submodule of M. And what else can we say? Phi of M, right? So this is a submodule of M. This is a submodule of N, right? The image of an R module homomorphism is itself a submodule. And another bit of notation, definition, hom R Mn is the set of all R module homomorphisms. from M to N. All right. Again, in the case that we were talking about M and N being vector spaces, R being a field, this would be the set of linear transformations from M to N. You studied this before, right? Now, he makes some comments here. He says, any R-module homomorphism is also a homomorphism of additive groups. All right? So, stop right there. That's why we define kernel to be the additive kernel, right? You could imagine looking at the set of things which map to 1. Well, actually, you couldn't do that, right? Because 1 isn't necessarily even an element of N, is it? 1 is an element of the ring, but N is a sort of a vector space. Well, it's a set which allows action by R, but it's not R itself. So 1 doesn't even need to be an N. So pretty much, I think I have to look at the additive kernel, right? But because a R-module homomorphism is first a homomorphism of additive groups, right? What's that say? If the kernel is 0, what does it tell us about a group homomorphism? What's our theorem from 421? Yeah, it's injective. It's 1-to-1. So if the kernel is 0, the R-module homomorphism is 1-to-1. We get that just from group theory, all right? But he says a little bit more here. He says, not every group homomorphism need be an R-module homomorphism. Why is that? Well, it's pretty simple, right? Just because you satisfy part A here doesn't mean that you satisfy part B, right? It's possible you can have a map as additive, but it doesn't allow you to pull out the R multiplication, right? So there's a distinction between just group homomorphisms and R-module homomorphisms, right? R-module homomorphism, it has more structure, all right? See if I can find an example in here for that. Well, he has an example on page 346. I'll let you look at it. Example 1 expands on that comment. Now, proposition 2, it says that phi is an element of Homer Mn if and only if phi from M to N is a map with phi of Rx plus y equal to R phi of x plus phi of y. So what am I saying there? I mean, proposition 2, part 1 is kind of a snooze fest. It's like, yeah? Okay, so what you're telling me is I can check conditions A and B at the same time, right? This is not particularly surprising. I mean, we did this for linear transformations too, right? A lot of times we would check both linearity and homogeneity at the same, we would just check linearity, not just, I would say that part 1 here, we're checking linearity of the R-module homomorphism, right? We're simultaneously checking, can we pull out the multiplication by the ring, and also do we have the additivity, right? If you put R equals to 1, you get additivity. If you put Y equals to 0, you get part B of the axiom, right? Because we can easily prove that phi of 0 is 0. How do we do that? Why is phi of 0, 0? Right? Which is by the cancellation property of additive groups, right? So just like linear transformations map 0 to 0, so do R-module homomorphisms, all right? Some things are different, but many, many things are the same as vector space theory. So part two here is this proposition has really, what is it?
I'm confused. Why did we do that?
Oh, it's his proposition 2, part 1. I'm just copying it down.
No, it's a 0 thing. Why did we do that?
Oh, so that I can so if I put y equals to 0 here, I get Rx equals to R phi of x plus phi of 0. So if phi of 0 is 0, this becomes, putting y equals to 0, this becomes part A of the axiom, of the definition of our module homomorphism. Like, knowing that phi of 0 is 0 makes this go away, and it just leaves us with phi of Rx equals to R phi of x.
So setting y equals to x shows us that phi of 0 is still 0?
Putting,
Is that what you're saying?
what I'm saying is that if I know this, I can prove part 1 of proposition 2.
Okay.
Because the proof is just putting y equals to 0. If y equals to 0, and I know this is true, then this is phi of 0, which is 0. And this just reduces to phi of Rx equals to R phi of x, which is precisely part B. Yeah. And to get part A from that data, we just do what? We just put R equals to 1. Yeah. Sorry. Now 2, in proposition 2, is much more interesting, I think, and really of a different nature. Here he says phi and psi, the elements of our module homomorphisms from M to N is what intelligent people would say. And so if that's the case, then guess what? Phi plus psi is also an element of this, all right? How do we define the addition of two our module homomorphisms? And also, R phi is an element of this, where phi plus psi of x is equal to what definition? And R times phi of x is equal to what by definition? I'll do the second one. R phi of x. So we just define scalar multiplication of a map by the pointwise rule that I just gave. So just like you learned in pre-calculus, we add functions by adding them pointwise, right? So what's my first definition that I haven't written down yet? It's phi of x plus psi of x. We have a winner, yes. So what does this mean? The set of homomorphisms from n to n, our module homomorphisms from n to n, the sum of two of such things is such a thing. A scalar multiple of such a thing is such a thing, right? What does that say about the set of our module homomorphisms? It is itself a R module, yeah. Because we have a natural additive abelian group structure, the addition of functions, or maps in this case, yeah. And we have a way for the ring to act on it by scalar multiplication, by, R phi. And if you check, you can go back to the axioms of a module, and you'll see that, yes, the homomorphisms, our module homomorphisms from n to n, itself forms an R module. Okay, so application hom R mn is a R module. Oh, there's more. 3. 3 is about composition. All right, so 3 says if you have phi going from m to n, and if you have psi going from n to, let's say, I need another letter. How about j? Both R module homomorphisms, then what? Then psi composed with phi, which is a mapping from what? Yeah, m to j is our module homomorphism. As we know, the composite of linear transformations is a linear transformation. Guess what? The composite of R module homomorphisms is an R module homomorphism. And then finally, part 4. And by the way, like proving 3, that would be a good example of something I would think is like totally appropriate for a test question, don't you think? I mean, here I can test, do you know what does it mean for it to be an R module homomorphism? It's not. What do you have to check? You have to check, well, if you use part 1 of the proposition, you can just check what? That the composite of Rx plus Y is R times the composite acting on X plus the composite acting on Y, right? So the proof is just to show that the composite has that. If you can show that, then you've shown that the composite is an R module homomorphism, right? And then 4 concerns maps from a module to itself, all right? Sometimes those would be called endomorphisms. So here, I talk about home R M to M. And with the addition and multiplication given as function composition, he points out that this forms a algebra. I'm sorry, an R algebra. What does that mean? So that means that there's an addition, all right, and there's a multiplication of the objects. The addition is just, function addition like we defined in part 2, all right. The multiplication is the composition of functions, right? So if I had like phi and psi in here, then phi times psi is by definition phi composed with psi, all right? So like composition is the multiplication here. And to be an R algebra, what does it mean? That means you have an R module that what? Oh, I'm sorry. I'm an idiot. It's not that it's an R algebra. It forms a what? Oopsie. A ring with unity. Actually, we need that R is commutative for this to be an R algebra. All right? Yep.
So you said like the quote-unquote multiplication is composition of functions, and you
Right.
said the addition was like what?
Just like this, just the usual addition of functions. Yeah. So this is a ring with 1. What is the 1 in this ring? In other words, if phi was equal to 1, then we'd have what? We'd have like phi psi equals to psi and psi phi equals to psi for all psi. Which map is that? The identity map, right? So phi of x equals to x for all x and m is the identity here. So it forms a ring with 1 in the sense that we can add or multiply functions and they satisfy the axioms of a ring. All right. Furthermore, this is also sometimes, he says, well, we can also just say that this is the endomorphisms, the R module endomorphisms of M. This is another notation. So if you see that later, that's what this means. All right? So-called endomorphisms. All right. All right. how would we prove that the kernel or the image is actually a submodule? I just said that. I mean, I wrote it on the board. How would you actually prove those things I just said? Yes. In fact, so basically, Bethany is proposing that we use the subspace test, but the subspace test has new trappings. It is now known as proposition I will eventually find my way back to. Come on. The submodule criterion, which is proposition 1 on page 342, which tells us essentially what Bethany was just telling me, which is that to check that something's a submodule of a given module, we have to check two things. One, it's a subset that's non-empty, all right? And two, that a linear combination, well, x plus ry is again in the submodule whenever r is in the ring and x and y are in the submodule, which is the one-step subspace test except for a module. So that's still how we do it. In other words, the proof I showed you in linear algebra is essentially unmodified. It's just now we are taking scalars from a ring as opposed to a vector space. Yeah? Or, excuse me, field. Sadness. All right, I will get back to where I was. Oh, come on. What's wrong with me? Many, many things. Come on. Here we go. Proposition 3. If R is a ring, M is an R module, let N be submodule of M, all right? Then M quotient N, right, can be given an R module structure. How? So R times x plus n equals something, and that's for all R in the ring and x plus n in the factor group. Here we're using the abelian group to form, this is an additive coset, right? This is with respect to the abelian group structure that's always there for us with an R module. So you guys, what's the definition that I haven't written here yet? Good grief. So fill in the blanks for me. What's the definition? Rx plus n, we have a winner, yes. And what do you think pi mapping from m to the quotient of m by n is? It's a, I'll do the first one, R module homomorphism, yes, all right. What's the kernel of pi? Exactly, it's x such that x plus n is equal to n, right? Because that's the 0 in the quotient, which is to say that x is an element of n, right? So what Liam said to start with is correct. The kernel of the natural homomorphism, the natural map is in fact, is just n. All right. The details in why that's true is it's laid out in the textbook. I'll let you read. Right? Many of these steps, almost all of them, look very, very familiar, right? We can also define the sum of two submodules, right? So sometimes this is nice to talk about. What's A plus B mean? It's just A plus B such that A is in A, B is in B. This is the sum of two submodules. All right. And he says that we could also prove that that is a submodule. So if A and B are submodules of M, then A plus B is likewise a submodule of M. And we could check that with the submodule criterion pretty easy. Again, operationally, the proof is identical to what you saw in 321, just the scalars are taken from a ring instead of a field, right? If you think about the proofs of, like, think about subspace proofs, right? Do we do division in those proofs? I'd be hard-pressed to find one where we end up doing division, right? So as long as division didn't really play a role, if it was just about the distributive property and commutativity of, like, the field of real numbers, almost all those things are going to transfer through to this context. Theorem 4 is the isomorphism theorems. So there are 4 of them. The first one is the one we emphasize in 421. All right. So it says if you have phi a homomorphism, an R-module homomorphism from M to N, then M mod the kernel of phi is isomorphic to phi of M. He also has recorded here the fact that the kernel of phi is a submodule. That's stated in the book as well here. And I usually make that part of the discussion in 421, right? The first isomorphism theorem, I'm a little bit sloppy about what I mean by that, right? Sometimes I'm just talking about what I wrote here. Sometimes I'm also talking about the fact that the kernel of phi is a normal subgroup, right? Although, in my defense, you can't write that unless kernel of phi is the normal subgroup in group theory, right? But here, we're talking about R modules, right? So every submodule is a module with which you can form a quotient, because the way we're forming quotients is with respect to the abelian group structure, right? And every subgroup of an abelian group has left and right cosets which are equal, which means we can form the quotient, right? So there's no, you don't run into that kind of quagmire we did in multiplicative group theory, where some of the subgroups are normal and some of them aren't, and you can only define division. We can only factor out normal subgroups, right? For groups in the wild, this is easier than that.
So it's included in the first isomorphism theorem that the kernel of phi is a submodule.
Yeah. I'm being lazy. Part number 2, it says that if you take A plus B and you quotient by B, then that's isomorphic to A mod A intersect B. This is the second isomorphism theorem. And again, here, A and B are submodules of M, right? Three, the third isomorphism theorem. This one's kind of easier to remember. It goes like this: M mod A mod B mod A is isomorphic to what? M mod B. We have a winner, yes. Also known as the unreasonable effectiveness of fraction notation for quotients. Because these are not fractions, but it looks like we canceled. Yeah, but there you go, we can prove that. And then 4 Really, any one of these would make, well, 2 or 3 would make a good homework question. All right? 4 is a little bit harder to understand. All right? N is a submodule of M. All right? And no, I'm just saying, well, no, we don't, I don't have a symbol for it. I just mean it's a subset and it's a module. But I said it in words. N is a submodule of M. But that doesn't mean that. No, that just means subset. I know, I'm sorry. I don't have any, I'm not in the, he's not in the habit of writing N less than or equal to M to mean submodule, like I was doing in linear. When I wrote like W less than or equal to V, that means W is a subspace of V. I don't have that kind of notation here. Yeah.
But if N is a module and it's a subset of M, it would necessarily be a submodule, right?
As long as it's a module with respect to the inherited module structure of M.
Okay.
I could imagine a context where you could come up with some other half-baked module notion, even for the same ring, but acting in a different way on a subset. It has to like inherit, you know. Here's the statement. There is a bijection between the submodules of M which contain N submodules of M which contain N. All right, what would that be? Something like, you know, N is a subset of B, right? It contains N, and B is an R module. And the submodules of M mod N. The correspondence is given by A. I guess I should use B, since I used B already. B, if it goes back and forth to B mod N, for all A which contain N. He says, this correspondence commutes with the process of taking sums and intersections. That is, the lattice isomorphism between the lattice of submodules N and the lattice of submodules of M which contain N. It's kind of a mouthful, isn't it? Aw, man, seriously? I thought I had another 5 pages printed. Come on. Curses. Have no fear. I do. Listen, you don't understand what I just wrote. And that's okay. Because this is actually the linchpin of Galois theory. Like, Galois theory is all about this and explicitly understanding how this makes sense. It has something to do with this. But I'm trying to think if I can... Oh, I'm sorry, my brain is fried. This allows you to take a lattice of subgroups. If you have like an abelian group and a lattice of subgroups under it, you can write down the corresponding lattice of factor groups by just crossing out things below the picture and by that group. That's implied by this, among other things. But if you don't understand this yet, it's okay. When we need it, we'll come back to it. It's something to be aware of. Yeah.
Okay. Yeah, so I'm just making sure bijection literally just, that would mean then it's not an isomorphism because we're not necessarily coming up with a function or anything like that between them, but it's bijection because there's a one-to-one correspondence between the two.
right? And this is the correspondence. That submodule of this corresponds to this submodule, which is containing n. But it's more than that. It also that this correspondence respects sums. So I think like if I had a plus b mod n, it would correspond to a plus b, and also intersection. So like a mod n intersect b mod n would correspond to a intersect b over here. So it's more than a little bit more than just what I've written on the board. This is less known, but it's a very powerful theorem. And if you really understand it, it will destroy difficult problems with blinding efficiency. So, yeah.
What did you say that you were matching the things in the subgroup lattice up to? It was like matching something? Or corresponding?
Here I'm saying, are you talking about what I'm on the board, or what I was saying about my comment to the subgroup lattice comment? So the subgroup lattice comment, the best thing I can do is send you guys an announcement with an example of it, because if I keep talking about it, it's not going to help. You just need to see it. Yeah. Yeah. A lattice, oh. I don't know, like Z10, right? So in there, there's subgroups. What are we got what? We could say maybe, was it 5? Is 5 Z10 something? How do I do this? Oh, be quiet. 0 and 5. There's also what? The 0, 2, 4, 6, 8. Right? These are the subgroups. So subgroup diagram, I might have called it. Sometimes we call it subgroup lattice diagram, sometimes also called. I think this is one's kind of boring, right? Then there's just, that's kind of it, right?
You mentioned these last semester when you were talking about ideals, and you worked with lattices then as well, right? Talking about principal ideal, not principal, principal ideals generated by a single element.
Yeah.
And prime versus maximum.
That is true. Yes. Not right. Of course, this is also a Z module, and these are submodules of this Z module because a abelian group is a Z module, right?
It's just like a subgroup diagram, and the lattice is just made of all the different pieces.
Yeah. But anyway, I'm sorry to scare you with 4. I should have just gone past it. It doesn't add anything to the course at the moment. I don't have any plans to do anything with it. My apologies. I didn't mean to scare you. Let's move on to section 10.3. Yeah. It's okay. I should accept my fate. After Monday, I should just give up. I think, listen, up till here, I have this general, ignoring, of course, the example from last time, the fx module generated by the linear transformation. That to me is I think that's a very interesting example and kind of surprising, that circle of ideas. This is kind of just, hey, it still works, / by the way, to actually prove 2 and 3, I think you can just use the first isomorphism theorem and the appropriate map. Calculate the kernel, apply it, something like that will do. If you're interested, I can get you started on those. But section 10.3, I think, is where we really start to see some more interesting ideas and start to really understand the distinction and yet the similarity to linear in a little bit more depth. This is called generation of modules, direct sums, and free modules, section 10.3. And so one of these we've kind of already done. What would n1 plus n2 plus nn, what would that be? each one of these submodules of a, I guess actually they could even just be sets. Yeah, these are just sets. I mean, the sum of sets is just defined to be. Yeah, exactly. I'm just using a different letter to spite you. Yeah, so just that's the sum of sets, right? If they were R modules, this would define an R submodule. We could check by the submodule proposition 1, right? We can also define RA. So if A is a set, and these are all, you know, and A are subsets of M, an R module, okay? AR or RA, we can define both of these things. What would these be? You might think just RA, where R is in the ring and A is in A, and then you'd be wrong. So this is by definition A1 R1 plus A2 R2 plus AN RN. And this one down here would be like R1 A1, you know, R2 A2 plus RN AN, such that what? Such that, of course, the A sub i's are in A, and the R sub i's are in R, and likewise down here. Now, if we're working with a left module, really only one of these would probably make sense, right? Which one would it be? Right. So this, I think this is the one we would focus on, this one, right? Because we're going to work with left R modules. So here I would need to define multiplication of the ring on the right. So I think the first thing I wrote is kind of irrelevant. Now, can you recognize, what is that? I mean, that's, if R is a field, what am I looking at? Our previous notation was this, right? Like in linear algebra, we called this the span. Right, so there you go. Now, what do you think is going to be a theorem? What do you think? You can tell me about RA. It's a submodule, right? So this is we're missing a mathematical wiseacre in here. So if there was one, they would be like, what about the empty set? What about that? Ah. So what do you think we define R times the empty set to be? No, everyone knows that you can't make nothing from nothing, but you can make something from nothing, right? So, but the something is 0. Now, I mean, right, the contenders here are empty set or 0. We'd like to put 0 there so that we can say that the span of any set is a submodule. Right? If I didn't put 0 there, then I'd have to rule out except when span of a non-empty set. It just makes things work together better if we do that.
So is that a construction, or is that what we...
That's a definition.
Okay.
Yeah. Now, in this case, we say that A is a set of generators for this submodule. All right? So if n is equal to RA, then n is generated by A. If A is a finite set, then what do we say about n? the terminology is to say that the submodule is finitely generated. All right, if there's a finite generating set, it's said to be finitely generated. What do you say if n can be generated by a single element? So if a if n is equal to r times, let's say, a single element a, right? Then what kind of submodule is that? It is a cyclic submodule. Very good. So of course, cyclic submodules are finitely generated, right? But not every finitely generated submodule is cyclic. Okay. Now, so the next paragraph here, he discusses perhaps some familiar concepts, right? Like, suppose you have a submodule and you know it's finitely generated. Then you might ask the question, what's the minimal generating set? If it's generated with 20 things, can I generate it with 19? Can I generate it with 18? Can I generate it with 17? Like how low can you go, right? Or given a submodule, and suppose you have a submodule that's just infinitely generated. Is it possible to find some finite subset of that which still generates it, right? We'd like to come to some sort of understanding and terminology to discuss when a given submodule could actually be finitely generated or not. Right, and to come up with some terminology to classify special kinds of submodules. All right, so that's where we're going in this section, and so it basically brings us to the topic of trying to understand linear independence and spanning, except over a ring. I mean, that's where we're headed here, right? And the theorem. Proposition 5 in this section, it characterizes independent submodules. So we'll talk about remember we talked about independent subspaces, and so if the subspaces are independent, then that means that there exists a isomorphism from the Cartesian product of the subspaces to the sum of the subspaces. So that theorem is still pretty much unaltered and available here. And then we'll define certain modules as being some modules. If a module has a generating set which is finite, let me say it this way. If a module allows an isomorphism to Rn, all right, then that's said to be a free module of rank n. But not every module is like that. So the story of dimension has some more nuance here. Anyway, it will not be something I can discuss in 2 minutes, which I don't have. So we'll come back to it next week. All right, guys? Thanks. Sorry I'm behind.